Okay, so let's read the problem. Okay, the beam is simply supported and loaded as shown. The beam is made up of 3 plates with 2 joints, joint A and joint B. I should have probably said small a and small b. It's really these joints, joint A, joint B. So it's an I beam. The width of the beam is 20. So 20 is basically in is I think it's this. The location of the centroid of the section is at C as shown. So the calculation for the centroid is already been done for you. So you don't have to worry about it. Otherwise, you'd have to do it like we did it for the P section some time back. The centroidal moment of inertia is 8.63 times 10 raised to negative 6. That's also done for you. Otherwise, you need to do it yourself by dividing it into 3 rectangular sections and then computing the inertia. A little bit of tedious calculation, but nevertheless important. So the inertia is given. It is 8.63 times 10 raised to 6 meter raised to 4. Find the average shearing stress at joint A and joint B at section NN. So two things going on here. One is we are told where exactly we want to compute the shear stress. We want it at NN. Okay, so now if you cut this section here, then this is what is at that section. And specifically, if in this I-beam, we want to compute what the stress is here and the stress is here, joint A, joint B. This should, joint A, joint B. Okay, we know that the shear stress is something like VQ divided by I times B. And we are already given what I is. We are given what B is. At least we'll get it from the geometry. Okay, Q is something we need to compute. Remember, it is integral y1 to c y dA. Okay, we can compute that easily. This V is at the section NN, right? Because we need to find the stress at NN. So we need to find V over here. Once we get the V, we can then use that in the formula. So pretty much everything is given, just a matter of doing the work of computing the values. Here, the first step will, why don't we get V first? Once we have V, we can get to other things. Okay, so in order to compute V, which is basically the shear force, we can draw the shear force diagram, but really we don't really need the shear force diagram. We just need the shear force at NN. So if we just compute that, we'll not draw the shear force diagram. There'll be another problem where we'll actually need to compute the shear force diagram. That is a more general problem where if you're asked to compute the maximum, the location where there's a maximum shear stress, then we want the maximum V. In that case, we need a shear force diagram. But for this one, we don't need a shear force diagram. So let's just draw the free body diagram. So there's 1.5, 1.5. It's nice and symmetric, which makes our life easy. Zero 0.2, 0.4, 0.4. Yeah, so left side is a pin joint, so VA, HA, and here we have VP. Because it's symmetric, right? The forces are, as well as the location of the forces is symmetric. It's easy to see that, well, first of all, HA is 0, no doubt about that, because there's no force in the horizontal direction. We can also see that VA equals VB equals 1.5 kilonewton, and they can just argue that's because of symmetry. So it was easy because We exploited the symmetry. Now let's compute the shear stress at N. Okay, so shear force at Nn. Okay, note you're not actually given the exact location of Nn. It's somewhere between A and 1.5 kilonewton, but we know that the shear stress is going to be constant across from A all the way to 1.5, right? Because it's not because there's no force really acting, shear force acting between points A and 1.5, so it will be uniform. So if you want, we can draw a free body diagram. So that's VA, which is 1.5. This is my section NN. Assume that the force is unknown. Let's call that V. And so we can see that VA minus V equals 0. So V is 1.5 minus V is 0. So V is 1.5 kilonewton. So we've computed the shear force at Nn. Okay. Next step is to compute the shear stress, now that you know the shear force. Okay, so we are asked to compute the shear stress at A and B. V is, well, the same shear force acts at A and B because it's a section. It turns out that I is given, it's the same for both sections, but Q and B are geometry related parameters. Q is integral y dA. So each of those points, A and B, could have a potentially different Q and different B. And so what we'll now do is we'll now solve, we'll basically solve for joint A, we solve it for joint B, and those will be the answers instead of trying to sort of diverge now from what we have so far. So I'm going to do it in two parts. First, solve for shear stress at A, and then shear stress at B. So first, shear stress at joint A. Okay, so let's draw the part of the beam which is at A. So I'm just going to go to the top part of the beam because that's the one which will determine the shear stress. So here is joint A. Okay, we are given some dimensions. I'll just put those. It'll help us later. It's 100 mm. Here we have this as 20 mm. Here we are given the neutral axis centered rather of the complete section. So that's the point C. Okay, let's see if you're given the location of the centroid in the figure. So if you zoom in here, you see that C is given to be 68.3 millimeters from the bottom. Here I'm trying to compute, let's compute this distance. Okay, so how to do that? Well, this is 80, this is 20, so it's 100. This height is 100 minus 68 point. So this is 100. So I subtract 68.3 from 100. One 31. So this is 31.7. And note that this is 10 mm. Oh, sorry, 20. My bad. 20. Okay, so let's just take that on the other figure here. Oh yeah, here. Look at this, this. This is 20. This is 31.7. And then this is joint A. Neutral axis. Okay, again, the formula is shear stress is V Q divided by I times B. Okay, so V is 1.5 kilonewton. I is also something we know, it's 8.63. 1 is -6. We just need to determine Q and B. So Q is integral y1 to c y PA. Okay, so the way shear works is that this part is going to shear off okay, so this part, the gray part is going, if joint A is to hold, then it has to be able to resist the shearing of the top part, which is the gray part from the pink part. Okay, so what we're interested in here is we want to compute Q for this part. So that would be, this will be Y. And then we need to do this integral from the bottom part, so 31.7 all the way to 31.7 to 20, so 51.7. So this could be written as YdA of 31.7 all the way to 51.7 YdA. Okay, so you could do that calculation. For that, you'll have to suitably take dA, split it into, it's a, you need to use basically calculus by writing dA as a function of dy and then doing the integral, but there's a shorter way to do this. What we have over here is basically the first moment of the area, which is this area, about the neutral axis. So in order to compute the first moment, all you have to do is we need to compute the distance of the y distance from the neutral axis. So that's the y distance. Multiply it with the area of the region in gray. Okay, so what is that? The y distance you can see is 31.7 plus 10, right? So when I say it's 31.7 plus 10, it's basically giving me the centroid of this particular rectangular section. It's going to be at a distance of 41.7 from neutral axis times the area. The area is 100 for the width and 20 for the height. Okay, that comes out to be, okay, so then I also converted that to meters, just so that everything is in meters. So to convert this to meters, it's going to be -3, right? Millimeters to meters, and this will be 10 raised to -6. Okay, so this answer comes out to be 883.4 times 10 raised to -6 meter cube. Okay, we got Q. Now we need to compute B. Okay, so we got Q, only left B. Now B is basically the width. Okay, the width, there are two options for the width. There is this one, B, which is 100, or there is uh, this B, which I think is, maybe it is 20. Yeah, it is here, 20. So we could choose one of the two, right? It could shear across, basically shears at joint A. So we could use B as this 100, or we could use B as 20. Which is the right option? Well, if you see this formula for shear stress as a function of all these parameters, uh, tau is inversely proportional to B. The smaller the B, the larger is the shear stress. So the larger shear stress is going to be at the pink part of the section. It's going to be at 20 mm, not at 100 mm, the gray part of the beam. Okay, so B will be 20 mm, and the rationale is shear stress is proportional to B. Choose a smaller B. So B can be either 20 or 100, and we choose this value, which is the smaller value. Okay, so from this, we see that small b, large. So the shear stress is V 1.5 times 10 raised to 3 Q, which is 83.4 10 raised to -6. I given to us already 8.63 10 raised to -6, and B, which is the smaller of the two values, 20 times 10 raised to -3 to convert into meters. So shear stress at A. So solving this gives me 725 kilopascal. For shear stress at B, all you'll do is you'll do tau B is V Q I B. Okay, I think V I've computed, Q I've computed. B would be, again, the same thing will hold true. You'll have two options. One option would be 60, another option would be 20, but 20 is the smaller of the two, so you will use 20. And then the Q would be, if you draw the bottom part, neutral axis, then this is Y bar, and then you'll have to compute this area. joint P. So Q would be this area, the gray area, times the distance of its centroid from the neutral axis. And the answer I got, and you should do this and check yourself, is 70 times 10 raised to negative 6 meter cube. The final answer for tau B is 608 kilopascals.